Hello and welcome back to my YouTube channel. My name is Professor Gavala, and today I'm going to be doing the third installment of the three-part series that pertains to the Fourier series. And in today's video, we're going to be doing this example, which states to find the Fourier series representation of the periodic square wave x of t shown below, right here. And the function is also depicted here. And it says to take t is equals to 1 and a is equals to 2. If you would like to pause the video and try to solve this, feel free to go ahead and come back and see how we solve it. In this video, I will be doing the entire Fourier series representation as well as plotting it in DESMOS so we can visualize it in real time. So based on what we know from our previous videos, again, please make sure to check out part 1 and 2 to understand what's really going on in the third part here. But what we're going to do is we're going to take that x of t is going to be ck e to the j k omega naught t, where ck is this 1 over t interval from 0 to t. X of t e to the minus j k omega naught t dt. All right. So again, this here is given, so we need to find ck, where we can say then that ck is this 1 over t interval from 0 to t over 2 times a e to the minus j k omega naught t dt plus 1 over t integral t over 2 to t minus a e to the minus j k omega naught t dt. Where remember now that this a is coming from here, right, from 0 to t over 2, and this negative a is coming from here, from t over 2 to t. All right. So what I'm going to say is that we have two cases, right? We have two cases. And the first case is when when k is equals to 0, right? So I'm going to say case number 1 is when k is equals to 0. And obviously the second case is when k is not equals to 0. But let's go ahead and look at the first case. All right. So then what I'm going to say is that C of k is equals to 0, or C of O, is equals to 1 over t integral 0 to t over 2 a e to the minus j times 0 omega naught t dt plus 1 over t integral t over 2 to t minus a e to the minus j times 0 omega naught t dt. What I'm going to do is I'm going to say that I know t is equals to 1. So take t is equals to 1. So then this becomes just 1. And here becomes 1. My parameters becomes 1/2. And my parameters here become 1/2. And here becomes 1. All right. So then we can go ahead and integrate this. We notice that this is a 0 here. So this entire term goes to 1. And this entire term goes to 1. So the integral of a dt is just a constant. So then c of 0 is simply a t evaluated from 0 to 1/2 plus negative a t evaluated from 1/2 to 1. This becomes a times 1/2 minus 0 plus negative a times 1 minus 1/2. This then becomes a over 2 plus this is basically 1/2. So minus a over 2. So then this becomes 0. So that's the key takeaway point from case number 1, is that CO is essentially 0. So when k is equals to 0, right, my coefficient is 0. I hope this makes sense. If you have any questions, please ask them down in the comment section below, and I'll be sure to get to you. So now let's go ahead and take case number 2. And this case is where k is not equals to 0. And it's a little more extensive, but we say then that ck is equals to 1 over t integral from 0 to t over 2 times a e to the minus jk omega naught t dt plus 1 over t integral t over 2 to t minus a e to the minus jk omega naught t dt. Let's simplify it for a t is equals to 1. So what I'm going to do here is essentially this just becomes a 1. This here becomes a 1. This here becomes a 1/2. And this here becomes a 1/2. And this here becomes a 1. So we can definitely go ahead and do this integral. And we see then that ck just basically becomes minus a over jk omega naught e to the minus jk omega naught t evaluated from 0 to 1/2 plus this becomes positive a over jk omega naught e to the minus jk omega naught t evaluated from 1/2 to 1. I hope we're seeing where we're getting this integrals from, right? This is just simply the integral of an exponential. What I'm going to do here is I'm going to bring this j to the top, so this becomes a positive. I'm going to bring this j to the top, so then this becomes a negative. And what I'll do here, next step, is say that ck is then equals to ja over k. And we know that omega naught is 2 pi over t. So t is 1, so then this becomes just 2 pi. So then I'm going to replace omega naught with 2 pi's as I keep going. So then this becomes e to the minus jk 2 pi times 1/2 minus e to the minus jk 2 pi times 0. Close that parentheses, minus, right, this minus here. Open it again, e to the minus jk 2 pi times 1 minus e to the minus jk 2 pi times 1/2. And what I'm going to do next is I'm going to notice that if I distribute this negative, let me use a different color. If I distribute this negative, right, I get that this becomes minus here and this becomes plus here. All right, so that's a pretty simple step. Let me go ahead and say that this here becomes a 1. This 2 cancels out with this 2, and this 2 cancels out with this 2. Now we can realize that this term here and this term here are the same, so we can add those up. So when we rewrite our ck, we say that this is ja over k times 2 pi times 2e to the minus j pi. And what I'll do is I'll bring this k out. All right. And then this is minus e to the minus j 2 pi. Again, similar thing. I'll bring this k out. And then minus 1. All right. So again, remember this term here is right here, and this term here is right here. And these two terms combine to give me this. Okay. So using what I know from the unit circle, we say that e to the negative I pi, which is Euler's formula, is located here, which is minus 1. And e to the minus 2 pi I is located here, which is plus 1. So then this just becomes a plus 1, and this just becomes a minus 1. So then we can go ahead and say then that ck is equals to ja over k times 2 pi. And then this becomes 2 times negative 1k minus 1k minus 1. But what we can say here is that no matter what this k is, this is always going to be 1. So then this becomes just a 1. All right. And to continue, we can then say that ck is equals to ja over 2 pi k. This is going to be 2 times negative 1k minus 2. If I go ahead and pull out this 2 from here, here, and here, I am left with a ja over pi k times negative 1k minus 1. Okay. So let's take for a case where k is negative. I'm sorry, k is odd. So if k is odd, so this is, let's say, 1, 3, 5. This becomes negative 1 minus 1, which is equals to negative 2. And for k is even, so 2, 4, 6, this becomes 1 minus 1, which is equals to 0. So what can we say then? We can say then that ck is equated to minus 2j, again, that comes from here, minus 2j times a over pi k, where k is odd, and 0 when k is even, and when k is equals to 0. All right. So then we can write our final solution. So this is the final solution here. X of t is the sum of k is equals to negative infinity, and it has to be odd to infinity. Ck is negative 2ja over pi k times e to the j times 2 pi times kt. So this here is your final Fourier series equivalent. If you got this right, good. If not, and if you have any questions, please leave them down in the comment section below, and I'll be sure to get back to you. So now let's go ahead and make sense of this equation. And in order to do that, we need to transform it into the sine and cosine domain. So what I'm going to do here is I'm going to say that this is equals to the sum as k is equals to negative infinity odd to infinity. All right. And let me go ahead and plug in my 2 for a. So this is minus 4j over pi k. And then Euler says that this becomes cosine 2 pi kt plus j sine 2 pi kt. So for any given k, if we wanted to write this all out as one function, so let's say like for any k is equals to x, k is equals to 5, or k is equals to 6, we can say then that the entire equation, the negatives and the positives, become x of t is equals to minus 4j over pi k times cosine 2 pi kt plus j sine 2 pi kt. All right. And then this becomes plus minus 4j over pi. Now, this is the negative case, all right, times cosine 2 pi kt. Actually, 2 pi negative kt plus j sine 2 pi negative kt. All right. So I'm going to use a rule that says that cosine minus x is the same as cosine x. and sine of x is equals to minus sine of x. So then this simplifies, right? So x of t, I'm going to do one term at a time. For this term here, we get minus 4j over pi k cosine 2 pi kt. For this term here, this j and this j become a negative one, and then this a negative here, so it becomes a positive. So we get plus 4 over pi k sine of 2 pi kt. All right, let me switch colors here. So then here I can change this to a plus per this rule. All right, this becomes a plus. This here is a negative and a negative, so it's a plus plus. So this becomes plus 4j over pi k cosine 2 pi kt. All right. And then last but not least, the last term here, this j and this j make a negative. But then this negative here brings out to be a negative. So again, right here. So I get a negative times a negative, so it becomes a positive. I hope that makes sense. Again, it's this j, this negative comes out. So negative times a negative is a positive. And obviously these are just pluses here. So then this becomes plus 4 over pi k sine 2 pi kt. All right. So then this becomes beautiful, right? This cancels out. This cosine cancels out with this cosine. So what am I left with? I'm left with x of t is equals to 4 pi k sine 2 pi kt plus 4 pi k sine 2 pi kt, which is obviously just 8 over pi k sine 2 pi kt. And this makes sense, right? Because all of our signal to begin with was a real signal, right? There was no imaginary in the signal. As a result, all my imaginary terms, right, especially the j terms, get canceled out, right? They leave the equation. So I'm just left with real terms. So my final x of t in the real or the sine and cosine domain just becomes the sum as k is equals to 1 odd to, let's just say, an n, 8 over pi k sine 2 pi kt. And this term here, you could plug into DESMOS and see how it reacts, which we'll do right now. But actually, before we do that, I want to make sure that when I plug this into DESMOS, I only get the odd values for k. So I'm going to say that k is equals to n, or 2n minus 1. And if you notice some examples, when n is equals to 1, right, my k is equals to 2 minus 1, which is just 1. Or n is equals to 2, my k is equals to 4 minus 1, which is 3. Or let's say I'm going to n is equals to 26. So my k is 52 minus 1, which is 51. So what I'm going to say is that on DESMOS, if I want to plug this in, let me say that n is equals to 51. What I'm going to do here is I'm going to say that x of t is equals to the sum as n is equals to 1 to 26. This is going to be 8 over pi. But now k in terms of n is 2n minus 1, right, from here. All right, times sine 2 pi. K again is 2n minus 1 times t. Okay, and this here is my final solution, and it's the same as this. So here, as you can see, I went ahead and plugged in that same equation, right? And you could type this in on your computer as well. And you're going to see that this is my first harmonic. If I make this 2, right? Again, this is 2 times 2, which is 4 minus 1, so 3. So this is my second harmonic. And you can see this is when k is equals to 3, right? So we got 1, we get 3, we get 5. If we want 5, we could make this a 3. And as you can see, it's saturating to a value here, 2, right? Again, if you remember our square wave where a was 2 and 2 and negative 2, right? Let me go ahead and do my 51. And as you can see, we're recreating that square wave, right? And this is what Fourier said, right? Fourier said, you give me any periodic signal, and I'm going to recreate it using the Fourier series, which is a very, very powerful tool, right? If you want, you can increase this as much as you want to. It might take some time. It's rendering, but it's gonna really saturate onto that 2 and give us a really nice value. Okay, if you found the video helpful, please give it a thumbs up. If you have any questions, please leave them down in the comment section below, and I'll be sure to get back to you. Please share my YouTube channel, and please subscribe to my YouTube channel. Thank you.